To welcome everyone. This is the second of 4 webinars of CUAHSI's winter webinar series on urban stormwater hydroinformatics. My name is Randy Diamond, and I'm really pleased to welcome Dr. Branko Kerkez from the University of Michigan Civil and Environmental Engineering Department for our second webinar. Branko is an assistant professor there at Michigan and received his education from University of Florida and UC Berkeley. So Branko, I'm going to let you take it and educate us all about enabling smarter watersheds.
Great, thanks, Randy. So I just turned the camera on to say hi, but I'll turn it off for the presentation and I can kick it back on when we do the question and answer session. So thank you very much for the invite. I'm really excited about the series and grateful for the opportunity to be able to present some of the work that our lab's been working on. So you see the sort of title here, which I think conveys a little bit what I'm going to talk about. But just to give you a little bit of background on our lab, we are kind of at the intersection between a lot of information technology and water. So what we try to do is we look at fundamental water challenges, and we sort of try to look at them through the lens of new measurement technologies, and so all sorts of widgets and data and all sorts of stuff like that. And so what you see here, like we robot real-time data collection and assimilation, and a lot of sensor networks. And again, we do that under the broader umbrella of water systems. And so, speaking of water systems, you know, I'm going to put this up. I know everybody has seen this before. It's a typical water cycle, but I kind of want to bring it up as a motivation about, you know, where we've been focusing a lot of our research efforts, it seems like, for a long time, and importantly so. And my background is sort of like in this area over here in the mountains. And so I worked for a long time before I came here to the University of Michigan on like what I'd like to think about as like pristine hydrology. These are really obviously like really complicated systems. They're in far places, and we've studied these catchments and watersheds, and there's lots and lots of work to be done there to understand them as complete systems. So it's an exciting area, but the one thing that's been happening, and the thing that I've sort of observed that I started working on here, is that surprisingly we know little, relatively speaking, in our backyard, right? In these systems, in these cities that are sort of part of the bigger water balance, but you know, we still need to learn about how the natural systems and these human systems interact. And if you sort of zoom into this region, what you'll see oftentimes is that urban water systems, as was really sort of well pointed out during the last series last week when Randy presented, are really these complex systems that involve natural hydrology, but a lot of human-made plumbing. And so if you look at your average city, it's going to be underpinned by, even for very small communities, hundreds of linear miles of pipes and tubes that sort of span the city, obviously delivering things like drinking water, but also in the context of today, serving for purposes of you know, stormwater management and sewers. And a lot of this infrastructure was built a long time ago. I think in a lot of American cities, it's almost 100 years old, right? It's been built at the turn of the last century. And it's so old, in fact, we have pictures of this. I think some of you might have seen these before. You know, I can have you guess which one was built in Roman times, but actually one right here, that's that old, right? We've been building these systems not too dissimilarly for a very long time. You know, we put pipes underground, we put all sorts of stormwater control measures, and naturally what will happen with this kind of infrastructure as it gets old is it gets stressed. And in a lot of places, it's actually getting so old that it's exploding, so quite literally. So this is a picture in Taiwan where a sewer pipe, I think the backstory is the sewer pipe basically filled with gas because it was clogged, and it exploded. And this is a common way that people who live in cities who might not be aware that, you know, there's pipes underground that serve an actual purpose. You know, this is how this invisible infrastructure becomes visible, is when it sort of breaks and we have catastrophes like this. So the stuff is obviously quite old, and it's being stressed beyond what it was oftentimes designed to do. And you know, when we look at urban stormwater infrastructure, I think people sort of interact with it in various ways, and it starts oftentimes on their street, as we saw last time. You know, you have these gutters, and there's all sorts of stuff going into it, not just water, but oftentimes pollutants and other things that build on urban environments. And when they sort of leave your neighborhood and they go down into these systems that start at potentially a small pipe that becomes the bigger pipe that becomes a bigger concrete culvert, and water naturally moves through these systems and can start sort of wreaking havoc in a lot of places. Like, you know, the urban stream syndrome is something that gets brought up commonly as one of the sort of impairments of urban water systems, but it's this idea that we're sort of eroding these natural stream systems that weren't traditionally subjected to these flashy flows. And the picture that people oftentimes bring to mind when they talk about this is this idea that, we've had traditional, we've had these hydrologic systems pre-development, like these green areas that have been converted to concrete areas that now lead from hydrographs that were more gradual to being replaced with something that's much, much more flashy. And this is sort of like the image that we always put up to sort of tell people how urban environments are changing and how bad things are. But, one of the ways I like to think about it is that we kind of wanted this. Like, we wanted to build systems like this. We didn't want water to sit around in urban environments. We wanted to get it out really fast. So we built these pipes and we built these systems to flush it out as fast as possible. And there's some great examples across the country where people have done that very effectively. You could argue if it was effective, but here's a city, here's a city in the US, like one that everybody recognizes from the movies, but this is the LA Stormwater Network. By a lot of estimates, Los Angeles will get something like 10 billion gallons of water during one storm during the summer. So just one storm. That's actually, if you look at the total water balance of the city, quite a large percentage of what they use annually. And they've done such a good job engineering the system that all of that water within about an hour and a half flushes out into the Pacific Ocean, right? So a lot of this water that could potentially be used, granted there needs to be some treatment and stuff for capture and direct reuse, is flushed out. So, it's a flashy hydrograph, but we kind of designed it to do that. We don't like to see water sitting around in ponds and puddles, so we get it out. And so, obviously capturing it would, as I said, require treatment, but also require storage. So if you store that water, you're going to cause flooding if you store it. So there's this trade-off, and what we've basically done now is we designed stormwater systems to just flush stuff out. So some parts of the country are struggling with, droughts, and other parts of the country are actually struggling with all sorts of flooding that's become more and more frequent. And this is a picture, I just kind of like it because basically shows this raging flood, and this person's just very inquisitively looking into it. I think this is obviously a very dangerous situation. You should not do something like this. And it turns out that actually, if you look at it, flooding is the leading cause of natural disaster deaths in the United States. And it's oftentimes not the kind of raging flooding that you might have seen in the prior picture, or maybe even river flooding. Oftentimes it's flash flooding in urban environments where you might have water pooling up underneath a highway overpass, and you have motorists that are just misjudging how deep that water is. And it leads to very, very unfortunate and deadly situations that, as I said, are kind of like something we don't want to see in urban environments. And so these systems are really being, as I mentioned, stressed beyond what they were designed to do. So there's the flooding aspect, but then as we heard last week, there's also a huge water quality aspect. In a lot of cases, a lot of the stormwater that runs off directly into ecosystems downstream, or in a lot of older cities is combined with sewer systems. And so when a lot of sewer flows get combined during a large storm with flows that are originating from rainfall, you get combined sewer overflows, which is that picture on the right-hand side here. So that's beautiful Lake Michigan being injected with a large dose of raw sewage. And I think, as a lot of us are well aware of, that those nutrients that are inside that sewage lead to situations like this. They lead to harmful algal blooms that are not just here in the Midwest and the Great Lakes, but you have them on the West Coast and the East Coast, and really sort of just wreaking havoc on a lot of these ecosystems. So when you put together the flooding and the water quality impairments, cities are not unaware that this is happening. They've known for a very long time this is a problem. And when you have a big problem, they oftentimes think of big solutions to address this. And this is the kind of designs you might see. So the idea being, if I have a big problem, I'm going to just build a bigger pipe to hold this. And I have to say, this is the kind of stuff, when I saw it as an undergrad, that got me into civil and environmental engineering, was the idea that you could build these massive projects. So the one you see in here is the city of Chicago, billions of dollars for a tunnel that effectively is trying to capture water at locations where you have problems, oftentimes downstream. And it's so popular, in fact, that tourists will sort of like go into these quarries that have been repurposed and take selfies in them. And while this is exciting from an engineering perspective, I think the reality is that most cities cannot afford this. So the kind of thing that got me excited to start working on this also led me to the sort of humbling realization that this is well outside of the scope for a lot of cities to be able to afford management solutions like this. And so when we look at a lot of smaller cities, they have to do it differently. And so the one I'll choose is just naturally, located in Michigan, where we are. So here's our school logo right here. It shows you that a community like Ann Arbor, which, 110,000 people, a relatively affluent community, frankly, is struggling with a lot of the same problems that a lot of other places are struggling with. The infrastructure that was designed, to handle this stuff is really not handling it. And so this is a picture of downtown. cities that cannot afford these massive tunnels, like we saw earlier, have to resort to other things. And this has sort of been I really think there's like a green infrastructure renaissance almost right now, is this idea that a lot of these distributed stormwater management solutions are brought into place now where you do not have the ability to build massive infrastructure. So what you see are things that look aesthetically appealing, like ponds and green infrastructure and things that have been dispersed throughout that the general public might not even know what they do, but they're there to buffer flows. They're like, instead of having one large tunnel, you're basically deploying lots of little buckets throughout a watershed to capture this and to convey it. And so when we look at the city of Ann Arbor, I'm just going to use this as a conceptual example. The idea is that you can sort of take these things and distribute them throughout a watershed. And this is a watershed I'll keep coming back to throughout this presentation. It's about 10 square miles, and the city is basically addressing problems as they occur throughout the watershed. So they might be flooding in a neighborhood, and they put in a stormwater control measure like this, a pond. They might have put some green infrastructure. And the idea is that as you're distributing these things throughout, and as you're putting them out throughout the watershed, you're somehow improving the watershed. Right? Because if I improve what's happening in one neighborhood and I'm going to improve what's happening in another neighborhood, somehow I'm improving the overall watershed characteristics. And then I think that assumption is at the heart of a lot of stormwater design these days, is this idea that I don't have the money to dig up the whole system, obviously, because it could be hundreds of miles of linear infrastructure. So what I'm going to do is I'm going to fix piece here, a piece there, and somehow it's going to fix the whole watershed. And that's something that we started wondering about when we first started working on is, is that really happening? Is doing something over here and doing something good over there actually doing something good overall? And to illustrate what might happen in this case is I'm just going to look at two examples right here. This is a conceptual example. So let's look at two neighborhoods where you might have installed something like this in the watershed. So what I'll do is I'll say I have neighborhood number 1, neighborhood number 2. They're flowing to some downstream location. Maybe it's the outlet of the watershed. And what I'll plot for you over here is sort of like a conceptual hydrograph. So when it rains in neighborhood number 1, you might get a flashy hydrograph like that, maybe some flooding. Neighborhood number 2, another flashy hydrograph, maybe some flooding. And then downstream they add up, right? So they're not in phase, so you're going to get some sort of cumulative response. Now the city recognizes there's some problems, so they go into the first neighborhood and they install maybe some green infrastructure, or maybe they'll install like a pond, and they improve that neighborhood. So that's good, right? They do the same thing in the other neighborhood. Now they're improving that neighborhood. And now what'll happen is if you're not careful, these things might actually add up now, whereas before they didn't, to cause a worse impact downstream. So there's a lot of studies, and one that really sort of opened my eyes was done by Claire Welty's group, where they basically ran a model for the whole entire city with stormwater control measures in place, and then one model with just pipes. Okay, something you would never engineer because that just seems absurd, right? And the model without those controls in place actually did better. So we have to be kind of careful, I think, to not run the assumption that somehow we're adding benefits together. In fact, in a lot of cases, they might not be adding up to a global optimum, nor they might actually be, causing worse things to happen. Now, of course, you can't guarantee what's happening, but it needs to be something that we need, we need to be mindful of these kind of things as we move forward, especially now in this age of distributed stormwater measurements, is this question of, are we really achieving system scale benefits, or are we just piecemealing these solutions together with the hope that, we're going to cross our fingers and they're going to work out? So yeah, I think the answer is still up in the air, but it's not something I hear discussed a lot. And I think it's really, really important, is this idea that we need to view these systems as actual systems. That's where our group sort of started coming up with these measurements. We sort of said, well, let's measure and see what this happens. And this is a picture I kind of show. I'm teaching a class on sensors once a year here at the University of Michigan, and I'm teaching it this semester again. And I pull up this picture always to show students how far we've come even in a decade or two about their ability to measure. So we had the, old school sensors like this that were sort of like not even analog, they were just sort of visual, to things that now can measure temperature and humidity for very low cost and give it to you in real time. And so this proliferation in sensing has also been accompanied by a lot of devices that allow us to get this data back in real time. So now we have microcontrollers and wireless widgets and all sorts of sensor networks that don't allow us to just take a measurement locally, but they actually allow us to send it out in real time. And I think that's sort of enabling all sorts of new things to be done within water systems, in particular measurements. And I think that's what a lot of people do. They sort of say, okay, this is great. I got a sensor. I'm going to go in and I'm going to take that data, and then I'm going to collect it over the span of a season or maybe a couple of rainstorms, and I'll analyze what's happening in my system. And I think that's really useful because it's enabling new kind of science, right? We're able to measure things that we haven't measured before, but we're still sort of in this thing where we sort of make our conclusions about the system later on. The thing that we've been pushing in lab for a long time is this idea that you can act on your data as fast as you collect it. So it is important to store data and analyze it later, but there might be value to sort of measuring it and processing it in real time so you can make some sort of decisions right away, like at the minute or second resolution. And that has a lot of ramifications, obviously, to things like flood forecasting. But the case I'll make to you, and this is the first study right here that I'll show you that got us into this, it actually can change how you do your experiments. So Randy was talking last week about measuring water quality, and this is obviously a really important thing. I think something that a lot of people are interested in. In the context of the Great Lakes, the big thing for us are obviously algal blooms. We want to see how runoff from a lot of these urban and agricultural areas is contributing to algal blooms, and so we want to quantify it. And when it comes to measuring water quality, we're not at a place yet where we have reliable sensors for a lot of the stuff that we care about. So in an ideal world, we would have continuous measurements for all sorts of parameters that we care about. But the fact is, a lot of things like nutrients and a lot of things like emerging contaminants, we just don't have good sensors for. So we can't measure something that we can just stick in the water and now we get like minute scale or second scale resolution. We actually have to still rely on these things that were shown last week during the seminar, which were like these samplers. So you basically have bottles. You might have 20 or 24 bottles in each one of these, and you take these samples throughout a storm, and then you analyze them later in the lab. And I contend that these are not going to go away, because even if you have sensors down the road, maybe in a few years for really interesting contaminants, there's always going to be emerging contaminants like bacteria and viruses and all sorts of other stuff where you're just never going to have a sensor. So these automated samplers are just not going away, but they come up with a lot of challenges. And for any of you who have used automated samplers, you know that they can be kind of annoying, because if you sample too slowly, like this thing is showing on the left, you might miss a storm entirely. So you might be trying to sample the pollutograph, and if you're not sampling fast enough, you might miss a storm. On the flip side, if you increase your sampling speed, you might run out of sample bottles before the storm actually goes through, which is also unfortunate because you might be missing dynamics of an entire event. Now, a lot of people have proposed ideas like, okay, let me sample based on flow weighting, or let me do something based on local sensor data. And that obviously improves it because you're sampling around the dynamics of the actual storm, but it still has its limitations because oftentimes these systems are flashy and the system might change so quickly that even just measuring a lot of local variables might not work. And so this is when we first started working on this idea that came around with, well, how can we use real-time data to improve how we do in sampling? So here you have our regular old auto sampler. It's gonna, it has a limited number of bottles. It might have like 20 bottles you can take samples for. And what we did is we basically connected it to the internet through these little widgets that we were building. They basically connected to the cellular network. They do what you would do manually, which is they check weather underground automatically. They say, is it about to rain? And then when that threshold exceeds a certain percentage, like, okay, there's like a 70% threshold for rain, we take a base flow sample. And then we measure the sensor readings in real time. We send them back to the internet when we run a real-time model of the hydrograph based on the system. And based off of that, we can optimize how we take samples. Now, that's sort of the high-level overview, but the idea is you're maximizing the use of these bottles throughout a storm event. So it involves some math that I'm not going to go into, but basically, anytime you want to work with real-time sensor data and real-time weather forecasts, you're opening up a whole new world of challenges where you have to deal with noisy readings, and you have to actually say, is the system actually changing, or is this noise? And so we were working on a lot of algorithms, and this was a paper that we published that I can share later if anybody's interested. But it basically allows you to say, I'm not going to sample based off of thresholds. I'm not going to sample based off of a predetermined kind of sampling schedule. I'm going to sample around the features of hydrographs. So I don't care how big that hydrograph is. It could be small. It could be really, really large. What I care about is I want to get a base flow sample with the weather forecast. I want to get the inflection points, the peaks, the recession limb. And that allows you to basically optimize your samples. And so that's kind of like what we put together, and then we deployed it in the field. And so this is Brandon. He's the first PhD student that actually worked in our lab, sort of showing some of the prototypes of this connected. So it's a regular old auto sampler, but this is an auto sampler that's connected to the internet. And going back to what I said earlier, why would you want that with scientific data? Well, it turns out that it can completely reshape how you do experimentation, because I can look at large flood events, for example, like the one that happened in Detroit in 2014. This was like one of those big storms that was never supposed to happen. Like statistically, it was an aberration, but it was a 2-day event. And if you would have sampled that event, like the water quality in that event, continuously throughout, you would have definitely ran out of samples throughout that. And what we showed is that you can basically, we captured the dynamics of that event based on the algorithm that was effectively for us running on Amazon Web Services that was sampling this stuff. And we discovered some really, really interesting properties for these hydrologic systems. We, for example, didn't see a first flush. We didn't see all these things that we were looking for, and the adaptive sampling sort of allowed us to really maximize the ability of the system to capture stuff. So real-time data is not just useful for kind of decision-making purposes like predicting flooding, but it actually can improve your scientific experiments. And that allows us now to say, if we have one auto sampler, for example, at the outlet of that watershed that I was saying before, now that this thing is connected to the internet and you're counting bottles and you know exactly what's happening, is we can have a web system that very seamlessly allowed us to maintain a large network of auto samplers with a very, very small field crew. So not only are you maximizing your bottles, but now you have a small team of students that can basically run around and just replace bottles as is needed, because we're just getting push notifications on our phone and a bunch of other things that are allowing us to basically maintain that system. And the whole goal was to say, okay, could we do this first of all? After proving that, can an undergrad do it? Then last summer, we actually had a high school student maintain a network of auto samplers and work for the Watershed Council. So technology plays, I think, the thing I'll say just to finish off on this is that technology is going to play a large role in allowing us to carry out much more comprehensive experiments and ones that allow us to stretch our resources much further than we would have otherwise. So that just shows you like sort of how we approach these problems, is this idea that real time actually makes a lot of sense. And once we started validating this, that actually got us to what the actual topic is of today's talk, which is this idea of, well, if you can control sensors, what else can you control? So we started scratching our heads around the idea of smart cities a couple of years ago, but we really didn't know what that meant for water, right? Because you hear about smart cities, you hear about energy, you hear about cars, but very few people are talking about water. And it's happening more and more so now. And this is the vision that we put forward, and this was part of an ES&T paper that we put out that basically said, okay, what if you had a city that was blanketed in sensors? You would have things like soil moisture sensors, rainfall sensors. You'd have radar data that was coming in. You would be measuring flow and volumes and all sorts of different things like water quality that would give you a real-time image of what's happening in your watershed. To really sort of like, if you will, like turn on the lights in the watershed and start seeing what's happening in real time. So is it actually doing what we think it was designed to do? Is it functioning like the system that we think it is? And then once you have that, is it enough to just measure, or can you start controlling things? So could you retrofit your infrastructure with things like gates and pillows and other things to actually reshape what's happening in real time? And that, I have to say, took a little bit of convincing when we first proposed this, because a lot of people weren't latching onto it. But I think we needed to kind of show that it would actually work. So the idea is, if we go back to the idea of these two neighborhoods that are somehow, unfortunately, the flows are adding up to give us some sort of undesired effect. So maybe they're spiking and there's some sort of flooding that's occurring downstream. Could you retrofit these sister systems with some sort of device that allows you to store water or hold back water? So for example, if we know it's raining a lot in one neighborhood and not raining as much in another neighborhood, could we use that extra storage capacity in the system to basically modulate the flows in real time? So really adapt the system on a storm by storm basis. So not say there's just infrastructure that does the same thing every time during a storm, but there's some embedded intelligence, if you will. And that's maybe not the best term, but really that's kind of like the one that's stuck with this, that decides how you operate these systems. And again, as we put the ideas out at the beginning, some people at the beginning were like, oh yeah, so I get where you're going with this. And some people were saying like, well, how are you going to do it? Is that really going to work? And it wasn't until we started building this stuff that it really sort of like the benefits, I think, sort of became apparent. So what we did is we started an open source project, this project that we call OpenStorm. And the idea is to sort of like lift the hood off of this and say, how do you actually build something like this? So a lot of the students in our lab will study, they study water resources, but they also get a dual training in electrical engineering and computer science that sort of allowed us to build this. And the idea was, could we build this for people so that they don't have to have this dual training, so they can just deploy it? And what you see here is essentially what we call a wireless sensor node. And what it is basically a stripped down cell phone. So you got a little cellular module or some sort of other wireless module that you want to get connected to the internet with. And then you have a microcontroller on here, a processor that's collecting readings from any number of sensors. It could be rainfall, depth, soil moisture, etc. All those readings get collected in real time and then transmitted out. And then the idea is you just blanket a watershed with these sensors because they're fairly cost effective, right? We built them ourselves, and you'd have like maybe one per square mile, maybe many more, right? It depends on the size of your watershed. Not only can you measure, but now we can also connect controllers. So we've been experimenting with all sorts of stuff. I mean, I showed the auto sampler earlier, but you can actually control gates and valves and pumps and all sorts of other stuff throughout a watershed. So this is really the hardware that enables the step of making this feasible. That was accompanied by a long list of developments related to the cloud infrastructure to support this. So what we've done is we've basically built an infrastructure that allows you to take in all sorts of sensor readings. These get processed in real time on the internet. We run everything usually on some sort of cloud service like Microsoft, but Google and Amazon and Microsoft, there's lots of different services out there for this. Doesn't really matter which one you use, but it allows you to visualize the data in real time and send out things like alerts. I was talking about flood forecasting earlier, and then it allows you to basically write apps in your favorite programming language to now control sensors, but also control actuators, right? And so all of this was put together. Through the support of CUAHSI, we actually hosted a workshop this summer. So just kind of back advertising what we did this summer. We had about 40, almost 50 people come to this workshop this summer where we said, we got this to work. We think it's doable now by other people. And you don't have to have like an electrical engineering degree. You can actually do this. And people came for 3 days. We had a really good time, like lots of academics, even like consultants and people from government. We taught them how to build these sensor nodes and how to deploy them over a 3-day span. And it was really from end to end. And it was quite a comprehensive workshop. And it seemed like it was well received. And we're going to try to do another one, maybe not next year, but the year after that. Because we wanted to show people what can you actually build using things like this. And what can you build? Well, here's a bunch of examples. So using these little sensor nodes, each one of these costs about $500. And that's like nuts and bolts included, battery included, everything included. These are like sensors that measure depth, for example, right? So you put them on a bridge, you put them on a pole, they can measure depth. This one shows you water quality right here. So we can measure things like continuous water quality measurements like pH and ORP and dissolved oxygen, and really those standard sort of classic continuous measurements. Fairly low cost again, and we just started deploying these. So through collaboration with DJ Seo down in Dallas, which you might be aware that Dallas has had some historic floods, but keeps getting them. So the historic is kind of a question. I mean, it seems to be regular now. We deployed, and we're currently still expanding this network, a flood forecasting system in Dallas, where you're taking real-time radar data, combining it with these low-cost sensors to really get measurements at a resolution that really wasn't conceivable before, either due to cost or due to the logistics associated with doing this. So this is being deployed currently. We kicked it off together, but right now it's undergrads kind of maintaining this network and deploying it, and we're scaling it out, and really not that expensive when you consider what it's giving you. It's a massive area. So that's the measurement side. But the thing that we've been pushing for a long time is the controls, right? So here's a picture of one of our valves. This is the sort of how do you control a watershed portion. You basically take a valve that was designed for industrial purposes. It's a butterfly valve. It's nothing like earth-shattering. It just doesn't exist on stormwater systems, right? And what we did is we figured out how to connect that valve to the internet. And we go into stormwater systems and we retrofit them. So here you see, for example, an outlet to a little basin that was there. Maybe it was a little wetland. The water would just flow in and flow out, right? That's how the system was designed. But by putting a valve on there and opening and closing it, you're completely changing how that system stores water, right? You can hold water in it, you can release it. And, for those of you who are kind of seeing this, you can kind of see what you can start doing here, right? You're completely changing how the system behaves on an event by event basis, right? You can have water quality improvements by holding that water. You can control local flooding, and you can kind of see the unit right here. Fully powered by solar power, everything's running off a battery, and it's connected to the internet. So the whole idea was to be able to retrofit this stuff very quickly and cost effectively. And this valve costs a few $1,000s. So it's really not that much considering how much volume you're holding back. We've been working on deploying these technologies through a bunch of places in the US. Most of the stuff was supported by the Great Lakes Protection Fund at the beginning, which was basically a very sci-fi proposal. I'm so lucky that they funded it because it basically enabled all these technologies. They allowed us to build it. All across the Great Lakes, I'll talk about Ann Arbor right now because that's the network that this sort of our biggest one. None of this would have been possible without collaborations of the cities, right? They allowed us access to the watershed, to the infrastructure. They really served as like collaborators in this, and they had a lot of good ideas. And as I mentioned, a lot of that early work was funded by a foundation that sort of like had I think a hunch that this could work, and they believed in it at the beginning, and that allows us to sort of like build stuff out like this. So here's that watershed that I was showing you earlier. It's about 10 square miles. We didn't know how many sensors were needed for this. I mean, it's kind of an interesting question, like how many sensors do you need to measure a watershed? Well, I mean, it depends on what you're trying to do, but also there's no good answer for that yet. So we just started putting sensors all over the place. So we started instrumenting the main trunk lines of the system. So it basically follows this like little boomerang shape right here. The flows originate here and they flow down to the outlet, which is number one. We're basically instrumenting about 80% of the flows and various things in there. So you have the valves in the system, you have various basins that have these valve systems, water quality, flows, and really sort of like going all out for the sensors with the idea that once we measure everything, we might actually know how many sensors are needed down the road in similar watersheds. This shows you one of the valve systems. So this is, I should probably like mute this. this basically shows you like one of the valves that went in. This is a 5 million gallon basin. That was basically a flow through basin. It was a flood control basin. It was originally designed. We put in these valves, and for a little bit of money, you can basically control these flows. So this shows you one of our undergrads deploy the system. So solar powered unit. You can see what happens when you open the valves. So there's 5 million gallons of water behind there. So if you just do the math of how much it would cost to build a new site that holds 5 million gallons, you got to buy land, you got to dig it out, you got to pay for engineering costs. It's really quite a cost-effective solution. It doesn't look like a lot of water is flowing out of it when we're opening the valve, but that's kind of the point. You decide what flow rate you want to achieve, right, on any given storm, which is kind of great, right? Because we know, for example, in this watershed, based on the auto sampler studies that we did before, if the flows are too flashy and they're too fast, they're just going to stir up sediment. And if you're stirring up sediment, you're increasing erosion, you're increasing phosphorus output and all sorts of nutrients and stuff. So it's kind of cool because you can actually set the flow rate through a little electronic device that's connected to the internet. You can hold flows back in this. So that's kind of the exciting thing. We've realized originally when we first started working on this, we're like, oh, well, flood control. But what we've soon realized is that flooding is only one benefit. Once you can hold water back, you have a lot of these biological systems like wetlands and settling basins that you can actually use to control water like we do in treatment plants. So imagine this image of a watershed that can effectively be controlled at a pretty high granularity to hold back sediments, to let them settle out, to really start acting like components in a treatment plant, which presents kind of an exciting opportunity because it basically says we can start applying all these lessons that we learned in water treatment that seems like such an industrial process to a whole entire watershed. And so to promote that kind of idea, what we started saying is, well, there's obviously all these local benefits that can be achieved. What can be done at the watershed scale? Because obviously now if you control it, if very fine granularity, you could be messing up the watershed even further at a system scale. So can we control individual sites to benefit the system? And so what we started doing was we looked at the site that we're controlling, and this shows you the site. This is like the valve that we located. We hold back water here based on whatever decisions we made back to open and close the valve. And what would happen usually before we sort of retrofitted the system for control, all these flows would flow down. This is about 2 miles downstream. They would flow downstream into this wetland that was constructed by the city. So this is a wetland that we didn't control before. Like if we still don't control it, that was never the intent. That wetland is obviously has limited size, right? So when it rains, you're going to get flows from this site, but also from all the neighboring sites. And what actually happens in a lot of situations, because it has limited capacity, limited volume, you're going to get overflows. So instead of flowing through the wetland and being treated, you have basically water that's overtopping right here, right? That's how the system is designed. So the idea was, could we put a sensor downstream, measure when that wetland has capacity, and actually only then send flows down. So basically saying, let's not control the site upstream just for its own benefits, but let's control it for the benefits of downstream. And so this is a study that we carried out about, I don't know, almost 2 years ago. This was like sort of like big for us just to showing that this works. You see the upstream basin right here. What we're doing is we're holding water. So now it's rained. It's about 24 hours after a storm, maybe a little bit more than that. And we're saying, okay, now that we know the wetland downstream is ready, let's send water down. And so what you see here are two plots. One is the water level in that upstream settling basin. This is what happens when you open the valve. Water level basically starts decreasing. And about an hour later, because the other side is kind of far away, slowly start the water levels. The water levels are changing in the wetland. When we first started measuring this, we again got kickback from people. They were saying like, well, how are you really measuring this? Are these acceptable measurements, et cetera? And we said, okay, well, here's a video, right? So now you hopefully have to believe that it's happening because there's a video of this system actually in action. So you can see the upstream wetland releasing water. And now what you're going to see downstream, hopefully it'll show in this video, are the water levels in the wetland. So you can see the water level start at that red line, and they're slowly changing as we're sending water from upstream, right? Just opening a valve basically at the time that we determine is necessary. It's basically showing, because it's not raining, we know that the only thing changing these levels could be that upstream site that's like quite far away. We're changing the behavior of this wetland because we're controlling a site upstream. And that's sort of like when you zoom out to the systems scale, you're saying like, well, I'm improving the wetland, but actually there's a cascading number of benefits that are going to be adding up as you start doing control, because you're effectively, by closing that valve in that basin, you're holding that water. So now you're settling out sediment, you're capturing nutrients, you're removing 5 million gallons of water without new construction from the downstream hydrograph. So you're completely removing it. And then later on, you decide to send it down. Instead of overflowing, now it's actually going through the wetland, whereas before it would have bypassed it. So just the addition of a single valve to one site can have cascading benefits that are adding up throughout the watershed, because we're basically controlling for system scale performance, not just for individual benefits. And so that was a demo that we did, and we were pretty happy with how that turned out, because it basically, we didn't even know if we were going to be able to measure watershed scale outcomes. And I think we're measuring them even further beyond that. I'll show you some more pictures of that. But basically, we're at a point now where we're saying, how can you how can you actually scale this? So the question I got from somebody about a month or two ago was like, okay, that works, but like, what do I need for a city like Houston? Like, how many valves do I need? How many sensors do I need? And the simple answer to that is, I don't know. But I think that's why it presents an interesting research problem. And I think the research problem that we're facing now is one that says, how do we take decades of knowledge, a century of knowledge about water systems, and embed it in something that computer algorithms can actually understand to do real-time control? So they can repurpose a watershed in real time to achieve water quality benefits or flooding benefits or some sort of multiple combination of this. So that's a big research challenge. And obviously the cities are not going to allow us to start implementing valves all over the place. We're not going to do 100 valves immediately. We need to show it's safe. So one of the things we've been pushing is the idea that we first need to simulate how control is going to happen. So can we take models of urban water systems, and ones that you might be familiar with are ones like SWIM, like the stormwater management model that the EPA makes, and show how you could control large systems like this? Well, it turns out that a lot of the traditional water models have not been designed for real-time control. That was never the intent, right? They're models that are designed to run continuously, and maybe you can do a little bit of control, but really not, you can't start applying fancy algorithms to it. So what we did is we've been working on a platform that's part of OpenStorm, again, open source, that allows you to stop the model on every time step and then apply external control logic to it to start simulating what would happen if you actually started having massive control systems. And that allows us to basically start applying algorithms from all these different fields to stormwater systems. And these algorithms are like really mathematical. And what I'll do is I'll sort of, like, for the sake of this conversation, just show you like briefly what's going on. But it's kind of exciting because we can basically engage with colleagues in other fields like artificial intelligence or self-driving cars and say, can the thing that's working on self-driving cars, that's driving these cars these days, that seems so palpable, right? Like, they're here already. And I mean, they drive outside my house, so I actually do believe they exist. Can we apply that to water systems? And if so, how do we do that? And there's a series of algorithms that's basically, that's come out of the machine learning literature or artificial intelligence literature that says, one way for a smart system to learn how to control itself is to basically give it control of the system and then see what it does. It'll hopefully learn over time. And there's a series of algorithms that were developed around this game called Breakout, and you might know this game. Unfortunately, the video is not showing up, but basically, I think some of you might remember this game. It's basically a bunch of blocks, and at any given point, you can move this paddle on the bottom, right? I promise I'll relate this to water. And at any given point, you got to decide if you want to go left or right so you can intercept this ball and basically get these blocks. And so at any given point, you're given the option to either move the paddle to the left or move the paddle to the right, and somehow you're going to achieve a high score in this game. The challenge becomes a little interesting because when you hand this over to a computer, how's a computer going to learn? Well, one way for a computer to learn is to just basically simulate this over and over. So it's going to play this game a million, a billion, a trillion times, because whatever, we have processors, right, who can do this. And after a while, it's going to learn what to do, right? So it's this trial and error kind of thing. So the idea that the computer, this agent right here, which I represented, this brain, but imagine this is a computer making decisions, is going to interact with its physical environment. And in our case, it's going to be the stormwater infrastructure. And it's going to try out a bunch of different things. So it's basically going to open a valve, close a valve, open a valve, close a valve. And after a while, it's going to determine what the best control strategy is based on the objective that you stipulated in there. So, obviously, we don't want to do that with real systems. We never want to hand over a stormwater control system to a computer and say, hey, learn by trial and error. But you can do that to a model. And the idea is if you can learn it onto a virtual model, then it can hopefully be transferred to stormwater systems. And the efficacy of this approach has actually been demonstrated in a number of different fields. And the video games were this first analysis. So this is a field called, some of you might have heard about this. It's called deep learning. It's this idea that neural networks can learn how to control any kind of systems. They showed it with video games where a computer basically learned through trial and error how to get the high score in a video game or play chess or play Go. And it does that by basically just taking a specification from you as the engineer that says, look, I want to reduce flooding or whatever. And then the computer over time learns how to control the system. And so that's effectively what he did. We took these algorithms that were designed for a completely different application. We said, can you apply them to stormwater systems? And that's what we did. We took our watershed. This is a sub-portion of that watershed. We built a model out of it. We retrofitted it with these, virtual valves. And then we said to the computer, go, like, just run the simulations over and over and just learn it. And that's kind of a really overwhelming problem, because if you think about a system that even has just 10 valves, right? 10 valves, and let's say you can only open those valves like 10% at a time. So maybe it's closed, 10% open, 20% open, 30% open. Think about the number of permutations that you had to run through in real time to figure out what the best control strategy. During any given time step, you have 10 to the 10 possible combinations. That's 10 billion combinations that you could run, and you got to figure out which one is correct. So obviously that's not that easy. And to do this, you have to implement all these modeling tool chains. And I'll basically save some time by saying that we've built our simulation framework into this kind of like reinforcement learning, it's called, approach, where it basically uses neural networks to learn what the best control strategy is. And it takes a lot of computational power. The only thing that's basically enabled this over the last few years are graphical processor units that are running inside computers that are really efficient. But even with the kind of systems that we're working on, it takes forever to learn the good control strategy. And I mean, forever to us is like a week, but basically we hand it over to the supercomputer and they're just crunching away. But ultimately, they learn a strategy, which is really fascinating. So you give it some valves, and what I'm plotting here is like how well the system is performing. So maybe we give it a reward every time it reduces flooding. And then we just hit it with a bunch of storms. And after a while, after a number of episodes, after about a week, it learns what to do. And the idea is that you can now take this and transfer it to a real system. So you model the real system in the computer, you hand it over, and what we're shown through simulation is that you can actually start controlling these systems to the kind of granularity that we were hoping for. So imagine the uncontrolled system before, so no valves, no real-time control, no sensors. Whenever it rains, it would do something like this. Now with a control system like this, the computer is actually controlling the watershed to achieve at the outlet of the watershed the kind of hydrographs that we only initially thought were possible, but we think are actually really possible now. And I'll show you some real-world studies where you rev it up and you keep it at a constant flow volume and you go down. So it's like a completely unnatural hydrograph. So we're not even talking about pre-development conditions. We're talking about like whatever shape you kind of want to turn it into. And these kind of tabletop shapes are kind of cool ecologically because basically we know, for example, in our watershed, if you keep it really flat and you don't exceed a critical threshold, like some level, you might not stir up sediments. So there's a geomorphically significant threshold that's not going to tear up the stream. It's not going to cause sediments to be stirred up. So if we know that about our watershed, we can just hand that over to the control algorithm and say, make sure it doesn't exceed that value. So basically starting to create hydrographs of arbitrary shapes. And so that's one way to do it. And so some of you might be thinking, well, I don't feel comfortable handing this over to a computer and a neural network to control it. And I think that's a very fair point. Like, we have to be careful about that, right? So we're also working in the lab on a number of other control algorithms. So if you don't like self-driving cars, maybe you think a jet engine or whatever, a jet like that can hover in real time over a certain surface is more reliable. And these kind of systems don't trust neural networks. They want much more physically driven equations. And I think I'm running out of time here, but I'll just tell you that we're working in those. We're taking watersheds and we're converting them to much simpler control systems. So you could make the argument that the only way to reliably control a system is if we really know everything about the hydrology, like all the pipes, all the soils, all the detailed things about the microbes and everything. But it turns out for real-time control, you actually don't need to know everything. And the best analogy I can make for this is everybody operates the shower in the morning, knows that you're going to find the perfect flow rate and the perfect temperature for you. And you're not going to do it using a perfect hydrodynamic model of of your household and the pipes and the temperature and all these different things. Instead, what you're going to do is you're going to tune that shower head until it gives you what you need. So basically, by using feedback, you don't need a really complex model. And this is what we've been doing for a really long time. We've been making complex models. You can develop a much simpler model that abstracts only away the simple components of the system. So we can take really non-linear systems like these watersheds and represent them as much simpler linear systems, like unit hydrographs effectively, that are adding up on top of each other. And because we're using valves, we can steer the system back to it. So whatever the model doesn't represent perfectly, you can basically like correct with valves, which is really interesting, right? So you don't need a perfect model. And so I'll skip the math. I'll just show you that there's a completely different class of algorithms that we're working on that does something that you might say hydrologically is too simple, like represent the whole entire urban watershed as a collection of tanks in series and in parallel of linear tanks. And it turns out if you do that, and I'm not going to go into the math, but I'll just show you that you can construct fully linear systems out of this, and you can start applying dynamic feedback control, which is a lot more physically based. It underpins like autopilots and airplanes and other things that I showed you about, to start doing the same thing that I showed you earlier, which is basically start creating, and this just shows you the model. I'd rather show you the actual results. you can start controlling entire watersheds in real time. So you tell us how many valves you need, and we can basically put them in there in simulation at least. I mean, we're obviously not there yet, and the real water systems control these. And so what we can start doing with these simulations, we can start showing like what's actually possible. Like how many valves do you need? Obviously, we don't need like to valve every single part of the watershed. And what we're showing through some of our preliminary studies is that if you take a watershed that might be like 2 to 5 square miles, oftentimes you only need 2 or 3 valves before the benefit of the valve starts decreasing. So basically the performance of your system starts leveling off after a while. So we have ways through these algorithms to basically decide how many valves you need and where you should place them, like these dark blue circles to do this. And so that's kind of exciting because it basically says we're starting to build frameworks from a research perspective to try to figure out what's possible and how to go about it safely. And if I could sort of like summarize this in one hypothesis, because oftentimes when you talk to cities, they don't really care about all the technical details. They might just care, what is this going to do this? And the hypothesis that I always sort of project to them is to say, real-time control, what it's going to do is it's going to take your system and it's going to shrink the size of the infrastructure needed to achieve certain goals. So for example, if I have a system like an urban watershed that's subjected to certain storm durations and storm intensities, any system, whether it's controlled or not controlled, is going to break at some point. So if a storm is really long or if a storm is really strong, the system's going to break. The hypothesis is that if you add these valves, you're going to push the performance zone of the system. So now this infrastructure that you had before can handle much, much bigger storms. Or on the flip side, if you're building new infrastructure, you can build it much smaller using real-time control. And so that's kind of what we're showing. Here I'm sort of showing the performance of the system. And think about these colors about like as flooding. So for example, if we look at flooding, if you have a really long storm and a really strong storm, the system's going to flood like this yellow area. What real-time control allows you to do is to push the performance of the system. So you get the system performing much, much like better during a lot of different kinds of storms. And to sort of put it in perspective, the line I'm drawing here, what we've shown is that a system like the urban watershed that I looked at in Ann Arbor, if it would flood every 10 years, now with control, it floods every 30 years. So basically a system that could handle a 10-year storm can now handle a 30-year storm using control. So we're working on these kind of equivalence metrics to try to put this in perspective with traditional solutions. So that's the thing. And so I'll just close off with this. I wanted to show you that even in the real world system, I'll show you some data, we can go from these kind of hydrographs. I mean, this is just a demo right here. I kept saying like we want to convert the watershed from something flashy to something that's more gradual, like a tabletop. We wanted to see this summer, can we create this tabletop? So we went ahead and we controlled our valves using all these like algorithms and some sort of more pragmatic things. And we showed in our system that you can do it. And again, for those of us who don't trust that our data is actually showing this, there is a USGS gauge at the outlet of a watershed, and the USGS gauge is actually showing that we can achieve these tabletop hydrographs. So no more is the system flashing and going back down. We're bringing it up to a constant level, keeping it below the erosion threshold, and sort of doing this stuff. And so that was kind of, again, a big milestone for our project, because keep in mind, that's just a bunch of students and a 10 square mile watershed. I mean, it's a pretty large watershed, and we can achieve these things. So the question was, what else can we do? And I walked into the lab one morning, and so what this is plotting is the water level at the outlet of the watershed. I saw the students were doing something like this with the valve. So this is at the outlet of a 10 square mile watershed. And I was wondering what they're doing, and they basically were trying to spell our school's logo in the hydrograph, which is kind of ridiculous, right? Because you're basically somebody sitting there at the USGS looking at this hydrograph and wondering what in the world is happening. And a student is sitting there like spelling their name or worse things in the watershed. And this might seem a little silly, but whenever we show this to the city, they recognize the value of this, because you can start spelling letters in a hydrograph. Imagine what else you can start doing, right? And so I think this is quite a powerful message, because it basically shows that you can start adapting these watersheds in real time given any particular storm. And so that gives us a couple of research challenges, I think. I think this is just starting right now. I think we're just scratching the surface of what's possible. There's a lot of challenges still, and those challenges relate on the creation of algorithms. So I think this is a really exciting opportunity for our community to engage with colleagues in electrical engineering, computer science, control theory, to really say, how does the knowledge that we have about water systems translate to some of these more automated algorithms? So I think that's a really big area that's going to see research for a long time coming. That's what we're interested in. I showed you 2 types of algorithms that we're developing, but there's just a lot to be done there to create safe systems, right? Another one is, no matter how perfect your hydrograph is, no matter how how good of a job you can do, I think, from an engineering perspective to create these systems, none of this matters unless you get the public's trust, right? So even the most perfectly engineered systems are never going to get adopted until we get the public buy-in. And I think this is really critical because as engineers and scientists, we have to be able to explain what we're doing. We have to put it into the context of existing solutions. And that means we have to, we have to work on figuring out how people perceive these things, right? Like, are they safe? Like, how's this going to change the flows in my neighborhood? What is this really going to do? I mean, frankly, a lot of people might be scared of an automated water system because think about the ramifications, right? They're directly tied to public health. They're directly tied to public safety. And we have to work on this now. We can't wait until this stuff is built to try to convince the public that it's safe. So I think that's a big challenge. And finally, I think we have a really big opportunity to train like a new generation of students that are going to be excited about both things. Because as you can see here, it's not just enough, to know about water. It's not just enough to know about sensing and technologies. We got to educate like students in a way that they appreciate all this stuff at the same time. Because I think a lot of these opportunities are at the intersection of disciplines. So I think that's possible. I also think with a lot of these kind of sensor systems, there's the opportunity to train a new kind of workforce of, if you will, like water technicians, like smart water technicians who are going to deploy these things, maintain them, replace batteries, like use iPads to maintain them. And I think that can provide a really rewarding career that pays more for a degree that doesn't require a college education. I think this is a way that we can sort of like promote equity and inclusion to provide techie jobs for people that would otherwise not have access to these things. So I'll just close with that, and I'll say that this research, as I said, originally was funded by the Great Lakes Protection Fund, but we have a new project that just launched this semester through the support of the National Science Foundation through their Smart and Connected Communities program, where we're basically trying to take these lessons that were learned in the Great Lakes and really trying to scale them out to the national level in collaboration with other universities, and you can kind of see them here, and industry and lots of other cities. Like the cities are really crucial to this. So with this, I'll just close. I'll say if any of this sounds interesting, go to OpenStorm. We've been trying to do our best to maintain this in our free time, and we've been trying to work with CUAHSI through these workshops. But presently, we're doing what we can to put this out on the internet. But anything you saw here is freely available for you to take and build your own stuff if you want to, but your own sensors, your own control algorithms. And I just wanted to put up the students because they're really the ones who made this possible. So everything you saw now was built by grad students, undergrads, and as I said, most recently high schoolers. And I think that's been really exciting. And all the photos and other things are on OpenStorm, and I'd encourage you to sort of join us on there and start contributing yourself. So with that, I'll close, and I'll be happy to take questions.
All right, if you have any questions, please type it into the chat box, and then we'll read it out loud and have Branko answer it. There have been a few so far. So the first one is from Charlie Stillwell. He says, most of your examples are concerned with hydrograph superposition downstream when using detention-based systems. How do you think the smart systems can inform other stormwater management strategies, such as infiltration-based systems or stormwater harvesting?
Yeah, I mean, great question. I think we're only one group kind of working on this. I think there's like Villanova has a couple other people who are looking at this stuff too, but there's not a lot of people working in it. It was really interesting. I guess I'll just give a long answer to this because I think it's really important. When we first started talking about this, it was a question of feasibility. And as soon as we show it, it leads to the questions like you just asked, which is like, what else can I do with it? And I think that's what's exciting about it is this is what we did so far, but you might already have your own ideas about how far you can take it. So by all means, by controlling a valve, you could improve the infiltration capacity of a site. Like we're looking at this in Toledo. You could retrofit green infrastructure. So we have 2 or 3 bioswales that we retrofit of the valve. You can promote better infiltration. You can promote the uptake of nutrients. You can start basically creating mini bioreactors with these things that are controlled in real time, which really was only possible in treatment plants up until now. Same thing, I mean, going back to the question about rainwater capture, the reason why we didn't do a lot of rainwater capture is because it requires storage. So if you're storing water and another storm comes in, you're going to cause flooding. With this kind of system, you could store that water, possibly treat it locally, inject it into the ground, or reuse it for irrigation. But beyond that, you can let that water go before the next storm. So you can really stretch the capacity of your system. So I think a lot of these kind of questions are like things that we want to look at, but also encourage other people to look at. So it's really cool stuff.
All right. Next question is from Jan Sitterson. I know you're looking at city watersheds, but have you considered the ecological effects of these valves on aquatic migration?
Yeah, so that's a great question. So anytime you can engineer something, you can also ruin it. And I think that's kind of what this question speaks to is if you're not creating a natural looking hydrograph, what are you doing? Are you messing with invertebrates? Are you messing with fish? Like, what are you doing when you're creating these systems? Because even with regular infrastructure, we knew that we went from a gradual hydrograph to one that's more flashy. That's bad. You know, what happens when you start writing letters and doing all sorts of other stuff? And I think the answer to this is we have to collaborate with people who really understand what's best for plants and what's best for animals and what's best for fish in these downstream ecosystems. And we should not be abusing these systems to create more problems, right? And so I think it leads to good collaborations downstream. It's going to, basically we have to figure that out, right? And the nice thing about these systems is, though, that you can create these things that give you these benefits. So if you know what's good for fish, we can try to create that. So, you know, it remains to be seen. So let's talk more about it.
All right, next question is, how do you ensure that the valves work when needed?
Good question. So I think that goes to the kind of question that a homeowner would oftentimes ask is like, what if this breaks? Is it going to flood my neighborhood? I think the answer to that is, like with any engineering system, they're going to be prone to failure. That's just what happens, right? You cannot avoid catastrophes overall. Some are just too big to be avoided. We try to take a number of best practices when building these systems. And it's something I didn't have time to talk about here, but basically you need to have a lot of backups. So every one of our valve sites has the remote control through the internet. If that goes out, it has local logic that opens the valve in case it can't connect to the internet. It has a button on the site, so we can go there and actually push a button to open it. And if everything else fails, it has a manual valve to help us do that. Now, you know, we haven't had any issues yet, but that's not to say that one day if there's a city that's got like 1,000 valves, that something's not going to happen. And I think that just says you've got to be aware of that kind of stuff. You've got to build that risk into it. You've got to figure out how to do it. I mean, even regular infrastructure is susceptible to it. The thing I always try to tell people is, you know, static systems like regular storm infrastructure, like that picture I showed before, was actually exploding, and it was doing that because we didn't know what was happening. So at least by adding sensors and valves, you know what's happening and you can go in and fix it. And, you know, from a broader research perspective, we have to build control algorithms that know when something is failing so they can use the rest of the system to sort of work around it. But again, I think this is a big research area. We're doing the best we can with cybersecurity and safety. But again, that doesn't mean there isn't room for improvement.
All right, next question is concepts applicable to enhancing quality of runoff flowing into drinking water resources, question mark.
So I guess since I'm talking, I'll restate that question and say, I'm assuming what they're asking is, can you treat runoff and make it a drinking water resource? I think with a lot of these like natural wetlands, especially these wetlands that have been retrofitted with valves, you can start doing a good amount of local water quality control. You know, you can also start doing aeration locally when you capture the water. You can start adding things if you want to. I think what they're looking at in places like California is injecting it back into the groundwater and letting that groundwater table do its own treatment, like we do with a lot of things. I think it's definitely possible. I don't know to the extent to which it will be implemented, but I think it's an area that's just like, I would encourage people to look at it, because my current answer is I don't know how it will work, but I know it should work and it probably will have good impacts. So.
All right, next question is how vulnerable are components to vandalism?
Yeah, that is a question I get. I cannot think of one time when I've talked about this where I haven't been asked about vandalism. And it's naturally what comes to mind, because I think most people who've deployed instrumentation have to worry about people stealing solar panels and messing with your stuff and all this other stuff. Again, it's susceptible to vandalism. It'd be silly to say that it isn't. But we know when it is. I mean, we actually have GPS tracking in all units, so we can see if it's been stolen or anything like that. It hasn't been that big of a problem. And, you know, the way I think about it is we have lots of other infrastructure that's okay. We have power stations, we have street lights, we have all sorts of things that are deployed out in the wild. Yes, people vandalize them. Yes, it happens. I don't think it's nearly as big of a problem as it might seem to be. But that said, we have to acknowledge it, and we still have to protect these systems when we build them, and we try to make them small so they're not visible. But then again, we also have to build control algorithms that can detect that something's been messed with, so they can like at least use the rest of the system to sort of be resilient to it. So it's a challenge, but I think our bigger challenges might be more in the research realm to try to figure out really just overall sustainability and resilience of these systems in real time.
All right, I think we have time for one more question. So next one is, how much of your work is informed by existing knowledge of reservoir operation, example, in river systems with multiple reservoirs? And then how different is what you are proposing?
Absolutely. So that's the natural inclination would be to say, like, there's a lot of work done on reservoir controls, a lot of seminal, like amazing work on controlling large river basins. Does that apply here? And I think the answer to that is we got to see, right? So whoever asked that question should check that out, because I think the hunch is it is, right? Like if we go from large river basins to these small systems, at the end of the day, the whole idea of optimizing these systems and using some sort of like, whatever is, in that literature, like optimization procedures like linear programming, integer programming, all these different things, I think it's doable. But you have to acknowledge the fact that the physics behind these smaller systems might be a little bit different. The timescales are really, really short. So a lot of time a storm can come and go within an hour for the whole city of Los Angeles, right? So you have to take that in consideration. So you got to consider noisy sensor data. You got to consider soil moisture. You got to consider like all these different things. And I think my guess would be that yes, they're applicable, but that has to be shown still. But I think again, that presents an exciting opportunity to take a lot of the like really awesome work that's been done in that area and apply it to these systems. So let's look into it.
All right, I think that is the last question. So I think we're done with your presentation, I guess. So I just want to give a note to everybody. We have another presentation next week on the 21st, same time, and it will be with Ben Hodges from University of Texas. And then this presentation with the recording and the slides will be online in a day or so. All right.
Awesome. Thank you, everybody.
Have a good day, everybody.